there are different types of radioactivity. Curie was focused on discovering different elements that gave off radiation. Ernest Rutherford and many others focused on characterizing the radiation itself. And so we've come to understand that the nuclei of radioactive elements are unstable, and what they do is they spontaneously decompose. And so they'll shoot out small pieces of themselves to gain stability. And so just like a lot of things where everything's trying to go to a lower energy to become more stable, these unstable nuclei are changing to become more stable. And there's several categories of natural radioactivity: alpha, beta, decay, gamma ray emission, positron emission, and electron capture. And of course, we're going to talk about all of them. Yeah. First, we're going to review something that you should remember from Chem 1A, nuclear symbols. So the nuclear symbol is this guy right here. The X represents the element symbol. You know, Cu for copper, Pb for lead, that kind of thing. Superscript on the left is the mass number. That's the total number of protons plus neutrons. And subscript on the left is the atomic number, the number of protons. I would like someone to explain to me why the atomic number can't be A and the mass number be Z, but they didn't do it that way. So anyway, this should be review. Most elements have several different isotopes. It is not possible to look at the periodic table and predict how many isotopes any given element has. Some new words: nuclide. A nuclide is a particular isotope of an element. We can represent the different isotopes or different nuclides by using that nuclear symbol. We can also use either the element name or the element symbol followed by the mass number. So you could have that indicates a particular isotope of carbon. It could also be indicated this way or this way. That's carbon-14. So if you see an element symbol or an element name and a dash followed by a number, that's the mass number. Because really the 6, we can figure that out from the periodic table. That's not that important. But it's the 14 that tells us which isotope of carbon we're talking about. And then we've talked about 3 subatomic particles: protons, neutrons, and electrons. These are the main subatomic particles. It turns out there's a lot of others. But these are the main ones that chemists are concerned about. These can also be represented with nuclear symbols. So P for proton, N for neutron, E for electron. The proton has an atomic number of 1. That's the number of protons. So it's 1 proton, right? And its mass number will also be 1 because a proton doesn't have any neutrons in it, right? And so here's the neutron. Its atomic number would be 0 because there aren't any protons, but the mass number is 1 because there's 1 neutron. And then the electron's really kind of fun. The electron has a mass number of 0 and an atomic number of -1. And we'll get to that in a minute. So is this coming back to you? You remember this at all? The one cool thing about this, the way the atomic symbol is if you want to know the number of protons, the number of neutrons, it's stacked up so that you can just subtract, and that's the number of neutrons. Isn't that awesome? And it's also bad math. Well, I didn't quite finish it. That was close. Okay, alpha decay. Sometimes symbolized with the Greek letter alpha. Alpha decay, we have an unstable nucleus that's emitting a particle composed of 2 protons and 2 neutrons. That is identical to a helium nucleus. And so here's the symbol. It's kind of small, so I'll write it a little larger. So we symbolize this as a helium nucleus. Now, a helium nucleus would have a charge on it, wouldn't it? Yeah. Well, in nuclear chemistry, we are not concerned about what the electrons are doing. And so even though a helium nucleus would have a +2 charge, they generally leave that off and don't even look at it. Because this is an area of chemistry where we don't really care much about the electrons. We're concerned about the nucleus only. Yes?
Does that take off with electrons? Or does it just take off as
Just the helium nucleus. So it's 4 protons. I'm sorry, it's 2 neutrons and 2 protons, a total of 4 particles, just like this little picture here, that gets spit out. Just zings off. There it goes. No electrons involved. Any questions? Yes?
So it's not actually helium nucleus, we're just putting a helium because that's what it has
Well,
the
it's
same thing
identical
as?
to.
Well, a helium nucleus
Looks the same.
is 2 protons and 2 neutrons, and that is 2 protons and 2 neutrons. So really, what's the difference between that and a helium nucleus? There is no difference.
So just imagining there's always helium attached to everything, so when it undergoes alpha decay, it's just losing its helium?
No, I wouldn't think of it that way. I wouldn't think of it that way.
Helium nucleus is
Yeah, nuclei do not contain helium, but this particle is identical to a helium nucleus.
Okay.
But do we see, I mean, that would be a helium ion then, an He2+ ion.
Oh, okay.
Have we done a lot of stuff with those? Do you think that would be very stable? No.
No.
Helium is a noble gas. It's got its 2 valence electrons. It's very, very stable as it is. So the only way you're going to get the helium nuclei is from radioactive decay, because you're not going to pull electrons off a helium atom.
It's very noble.
Very noble. So we write nuclear equations to represent nuclear processes. And the important thing about nuclear equations is that the sum of the atomic numbers on both sides of the arrow have to be equal, and the sum of the mass numbers have to be equal. This is nuclear chemistry, okay? In other parts of chemistry, we said that atoms are not created or destroyed in chemical processes. Okay, this is the exception. Atoms are being created and destroyed. So we're starting out with uranium, and through radioactive decay, we're ending up with thorium. The element is changing. And that's like so different than the rest of chemistry, where we've just hammered into you, if you've got a uranium atom on one side, you have to have a uranium atom on the other side, right? You have to get around that. What we're concerned here is that the mass numbers, total of 238 on the left, 234 plus 4, 238 on the right. The atomic number, 92 on the left, 90 plus 2 on the right. So the top numbers and the bottom numbers have to add up to the same value on each side. That's how we balance a nuclear equation.
So it's actually skipping over one in between.
Right, it's because it's losing 2 protons. And so it is skipping over the next smallest element. What is that? PA. I can't remember what PA is. Palladium? No, I think palladium's PD. Somebody's going to look it up, I know.
So what happens to that helium that decays? Where does it
What
go?
happens to this helium nucleus? It zings out.
It just flies around the universe? Does it try to look to attach to something else? Or
It's
Protecting them.
it's most likely going to ionize something else. And depending on what it runs into, it could cause a great deal of damage or not really mess up anything at all. And we'll talk about that in a minute as well.
So we get our stock of helium.
No, this is not a good way to get helium. In nuclear reactions, elements often change their identities. So that's important to remember. So let's write the nuclear equation for the alpha decay of polonium-216. So PO216. 216 is the mass number. We need the atomic number, so we're going to have to find it on the periodic table 84. And if you notice, the mass is in parentheses because it's an estimated mass. This polonium's radioactive. There is no stable nucleus, stable isotope, and so it does decay. So alpha decay, that tells us that one of the products is an alpha particle. And you do need to memorize what these particles are. So it's going to give off an alpha particle and something else. So we know that the mass numbers of this and the mystery thing have to add up to 216. So it's going to be 216 minus 4. The mass number of the daughter nuclide is going to be 212. And 84 minus 2 is 82. And so we find 82, and that is lead. Any questions?
It's not pure lead, though? Or is
It is lead. It's an isotope of lead.
a nice
Yep. I forgot to mention something on this previous page. The parent nuclide and the daughter nuclide. So the parent comes first, and the offspring is called the daughter. So any questions about this example? You should have done stuff like this before. Might have been a while. So a good way to remember some of the characteristics of the different types of radiation is to think about vehicles and traffic jams. Okay? So alpha radiation is the 18-wheeler, the semi-truck of radiation. It is big. Okay? So it can cause a lot of damage, but its penetrating power is very low. So it is the most massive particle that's emitted by radioactive nuclei. It has the highest ionizing power, but the lowest penetrating power. Ionizing power is the ability of radiation to ionize other molecules or atoms. So, mentioned earlier, this helium nucleus, alpha particle, is not stable itself, right? What would it take for it to become stable?
2 electrons.
2 electrons. If it grabs 2 electrons from something, it's going to become a helium atom, and then it'll be nice and stable. It's going to grab electrons from pretty much anything it comes in contact with. So if this is inside of a living organism, this can cause a lot of problems, right? So it ionizes other molecules or atoms. This can cause damaging chemical reactions, which can result in cells dying or in cells reproducing abnormally, which we call cancer. So high ionizing power, this stuff can be really dangerous. But the penetrating power is very low. Penetrating power is the ability to penetrate matter. Radiation has to get into a cell in order to ionize molecules within the cell and cause real trouble. And these alpha particles don't get through much. So if you think of a traffic jam and a semi-truck stuck in traffic, it's not going to have much luck getting through. It's just going to have to go with traffic. It's not going to be able to switch lanes and get through. We'll talk about one that's a motorbike later. Motorbikes get through really well because they can just drive between the stopped cars, right? So these alpha particles can actually be stopped by a sheet of paper, by your clothing, by a layer of air. Almost anything will stop these guys. So if alpha radiation is outside your body, not a big deal. If you inhale it or ingest it, though, and it gets into your body, then it can cause a lot of trouble. So that's alpha radiation. Beta decay. Here we have an unstable nucleus emitting an electron. Does that bother anybody? Are there electrons in a nucleus? What? Technically, I don't have electrons. What happens is a neutron turns into a proton plus an electron, and the electron leaves. It's a little hard to get your mind around. So, I think a lot of chemists, we like to think of protons, neutrons, and electrons as being indivisible, indestructible little particles, right? Kind of hard to understand how they work and stuff, but they're just these little things that can't be destroyed. Well, it turns out you can smash them and break loose all kinds of other little particles. There's bosons and muons and gluons and all kinds of stuff in there. So you can break a neutron into a proton and electron. So the nuclear equation for that goes like this. And now we see why the electron has an atomic number of -1. Because an electron plus a proton equals a neutron. And so this is an example of beta decay. Here we have radium-228. It decays to actinium-228. There is no change in mass number, but there is a change in atomic number. The atomic number actually goes up 1 because a neutron has been changed into a proton. So the number of protons increases by 1, and 89 minus 1 is equal to 88.
And by the arrow, it can't change back, it only goes one way.
These are one-way things, yeah. These are not reversible reactions. Hmm?
But then it can lose helium. Or it can lose.
Well, it could go on and lose other things. Yeah, and they will. Because actinium-228 is probably not stable either. So, here's an attempt at a picture of this. Carbon-14 can also undergo beta decay, becoming nitrogen. So, yeah, carbon can turn into nitrogen. So, what were the alchemists all trying to do? Turn things into gold, right? Well, is it possible to turn lead into gold?
Yeah.
It is. Is it cost effective? No. No, it's not. So beta radiation, the four-door sedan of radioactivity. Beta particles are less massive than alpha particles. So their ionizing power is lower, but their penetrating power is higher than alpha particles. They can be stopped by a sheet of metal or a thick piece of wood. They're more dangerous outside the body than alpha particles, but they're less dangerous inside. They're not safe, but they're less dangerous. Gamma emission, gamma ray emission. So this is different than the alpha and beta decay. Those were actual particles. This is electromagnetic radiation. Yeah. Gamma rays are high energy photons. So gamma rays have no charge and no mass. So the mass number and the atomic number of the element don't change. The symbol is gamma with a superscript and a subscript of 0. We usually see gamma ray emission in conjunction with some other type of radiation. There may be beta decay and gamma radiation as well. Oh, yeah, right there. So here's an example. In the decay of uranium-238 to thorium-234, what's the name of this particle? Alpha particle. So we have alpha decay and gamma ray emission. So gamma rays are the motorbikes of radioactivity. They have the lowest ionizing power. They're very small, right? They're photons. But they have the highest penetrating power because they can go through a lot of stuff. To stop gamma rays, you need several inches of lead shielding or thick slabs of concrete. It'll go through a regular brick wall, no problem. It would go through one of those vests at the dentist's office. That's not several inches of that lead. That's maybe half an inch of lead.
What happens to this ray in several inches? Does it back out? Does it bounce around?
That's a good question.
Absorb?
I think it gets absorbed.
It stays there?
Well, I mean, what are these? This is energy, right?
Yeah.
And so it's going to be absorbed by something. It would probably heat up the concrete or the lead, yeah.
And how can we tell just by looking at that we know that the gamma rays emitted?
That's a good question. How would you know? You wouldn't. That would be determined experimentally. They'd measure gamma rays being emitted. And so, like if I was asking you to write a reaction or an equation for the decay of uranium-238, I need to tell you it's alpha decay with gamma ray emission. And that's how you would know to put that in there. Because you can't tell just from looking at the product what type of decay it would be, because it doesn't change the mass number or the atomic number. It's just pure energy, basically.
So it's always zero.
It's always zero, yeah. Then there's positron emission. So you can think of a positron as being the antiparticle of an electron. It has the same mass as an electron, but an opposite charge, so a +1 charge. And if you collide a positron with an electron, they annihilate each other. Poof, gone.
Don't they do stamping? Don't they do it for stamping or particle accelerators?
Oh, they do all kinds of stuff at the particle accelerator. But when those two particles collide, the mass of them, even though it's teeny tiny, the mass of them has to do something, and it's released in the form of energy, gamma rays. So positron emission involves a proton being converted into a neutron and a positron. So one proton turns into a neutron and a positron. The positron is what's emitted, the neutron stays behind. So the mass number of the isotope is going to stay the same, but the atomic number is going to go down. So phosphorus 30, positron emission turns into silicon 30 with the emission of a positron. So a beta particle was an electron, right? A positron is going to have similar ionizing powers and penetrating powers to beta decay, beta particles, because it's the same mass. So is it a semi-truck, a four-door sedan, or a motorbike? It's the four-door sedan. I think it's funny that he says four-door sedan. Like, how does he know it isn't a two-door sedan? Maybe it's a sports car. Maybe it's a Cooper Mini.
Isn't the definition of sedan 4 doors?
Yeah.
That's probably, I don't know.
So why would you say a
This is someone who likes orange soda. So, you know,
that is
yeah. Electron capture. And this form of radioactive decay is different from all the other forms because all the other forms involve the emission of something, whether it's a particle or energy, and this involves the capture. So we have a particle being absorbed. So the nucleus is absorbing or assimilating an electron from one of the inner orbitals of its electron cloud. Now, mathematically, this chapter is much simpler than the previous chapters. Conceptually, yeah, your brain might spin a little bit.
Are there videos on this?
I'm sure there are videos on this.
I like it when it's one or the other, either hard math or hard concept, not both.
Yeah, so this
There's
is,
so much to get hung up on.
right, that's true. We have to look on the bright side of everything. So this is a particle being absorbed. The net effect is a proton being converted into a neutron. So we've got the proton plus the electron forming a neutron. The electron came from the electron cloud. But the nuclear chemists don't care about the charge on this atom or ion. So they're not going to keep track of the electron disappearing. But this is the opposite of what?
That is the opposite of positron. Yes, opposite of positron.
Yeah, or the one that gets spit out.
The opposite of this one, right? Beta decay.
No, it is.
So the neutron decomposing into a proton and an electron capture is a proton plus an electron turning into a neutron. And the positron emission is similar in concept, but it doesn't involve an electron. Where was I? No, we did that. Did that.
Totally different branch of chemistry, it doesn't cross over to the.
Well, it does cross over, but some of the things that are true in chemical processes are not true in nuclear processes. Because in a nuclear process, energy can be converted into mass, and mass can be converted into energy.
So what practical applications would a nuclear chemist be doing?
Oh, all kinds of stuff.
Cancer research.
Yeah, there's all sorts of nuclear medicine things that you can do, but, you know, obvious things are nuclear power and making of bombs. And also just trying to understand matter better. So when we have this electron capture, the atomic number decreases by 1. So we have here ruthenium-92 plus an electron. That electron converts a proton into a neutron. And so the atomic number decreases, the mass number stays the same. Yes, and we will talk about carbon dating. Here's a nice table from your textbook. I'm not going to read it to you, but that helps compare all these different things. So let's write 3 nuclear equations to represent the nuclear decay sequence that begins with the alpha decay of uranium-235, followed by a beta decay of the daughter nuclide, and then another alpha decay.
Nice.
It was fun?
Uranium-235 weapons grade?
So, I don't think it matters if it's weapons grade or not. We should be careful what we talk about so that we don't get censored again on YouTube.
Do we get censored?
Well, YouTube thinks that my Chem 20 videos for Tulare contain content that might not be appropriate for all audiences.
Someone reported it?
Terrorists.
Well, no, it has like these automatic things, and I don't know what it
I
says.
think that means someone reported it.
I don't think so, because it happened immediately when I posted them. I couldn't see them. It took me a while to figure out that I had to turn off my safety mode, which I didn't even know was on. And there they were. Yeah, very weird. It has happened to a lot of people. So here's the uranium-235. I found the 92 on the periodic table. Beta decay. No, alpha decay first. So alpha decay first. What is alpha particle? It's the helium nucleus. So 4, 2, He. And then we'll just, this is just real nice simple math. We've got 235 minus 4 is 231, and 92 minus 2 is 90. Then we look up 90 on the periodic table, and that is thorium. So this is the daughter nuclide of the alpha decay of uranium-235. And then it wants us to look at the beta decay of this daughter. So I'm going to write it as a separate equation. 231.90 thorium. Beta decay, what's the beta particle? Electron. So this is 0 and minus 1. And so our numbers here are going to be 231 and 89.
89?
No, 91.
91, sorry. 91. And 91 is PA. Anybody look up what PA is?
Yeah, it's,
You looked it up and you forgot it already, didn't
I
you?
told you, yeah.
Oh, you're right. Dang it.
Protactinium.
Protactinium?
Protactinium, yeah.
Okay. Interesting. So, protactinium, 231. And then another alpha decay. So taking this protactinium, 231, 91, PA. Alpha decay tells us helium nucleus, alpha particles coming off. And so 231 minus 4 should be 227. And 91 minus 2 is 89. And that is actinium.
Actinium.
Okay, any questions? So you need to have the symbols for these particles memorized so that if I tell you what kind of decay it is and give you either the parent or the daughter nuclide, you can write out the equation. Or if I give you the parent and the daughter, you can look at what changed and identify what type of radiation was given off. The
So I
gamma
have to
rays,
memorize.
Yeah, we could just like gamma ray,
Gamma-
okay.
gamma rays, yeah, those just come out whenever they want to, basically. You can't really predict it from these sorts of symbols. Oh, really? That was A? Oh, I guess that was A. Look at that. There's more. Okay, how about positron emission of sodium-22? So sodium-22. That's 11, right? Yeah. So positron. The name positron is a lot like electron, right? So the positron is an electron, but it's 0 and +1 instead of -1. Same mass, opposite charge. So it's still 22, but now the mass number has gone down, and so that is neon. Yeah.
Neon?
Right?
Sure.
Yeah, I'm sure. There's a big old blue number 10 above neon. Here, I do.
Sure, why not?
Why not?
Can't miss that.
Okay. Everybody doing okay? This isn't that hard. Not compared to the whole weak acid titration business. Krypton 76. Atomic number of krypton is 36. Electron capture. All the other ones were emission, so the particle gets written as a product, but this is capture. The particle is a reactant. What is the reactant? It's an electron, right? So electron has a mass number of 0 and a charge of -1, an atomic number of -1. And so then you just add the superscripts and subscripts, and you get 76 and 35. It's bromine, right? Bromine. So the subscripts on the left add up to 35, and the subscript on the right is 35. Again, watch those negatives. They're pesky. Any questions?
What'd that turn into?
Turned into bromine.